Okay, let's get started. Okay, make sure the recording is good. Okay, perfect. So this week, as advertised earlier, we are finally doing the actual quantum version of the Mermin experiment. I know we've beaten this thing to death. It's been, I think, this is almost like the third tutorial. But we've been working towards it. So we're finally there. Actually, going to implement it in Qiskit this week, and then see how that actually works. I'm not going to do like a preamble on it, just because I'm assuming most people by now hopefully know how the experiment goes. There's different cases, whether the same or different. There's three different settings, there's two different like lights, either like red or green. So we're going to actually try and encode that in Qiskit based on the rotation matrices and block spheres that we worked on last week. So I will just do a brief overview for anyone that missed last week or needs like a little refresher on what happened last week. I'm using Dr. Sabri's slides, but I'll try and annotate as we go. Basically, we have a representation of a like quantum like qubit that we've been talking about in class, and we can represent a single qubit as being located on a 3D sphere, and we call this the surface of a 3D sphere, and we call this the block sphere. Now, doing operations in this sphere, generally we have the computational basis being along the z basis, so the zero like classical bit is at the top, one is at the bottom. But any other like operation or gate that we'll do is represented as some sort of rotation around this around this block sphere. So Hadamard rotates, I think, 90 degrees around the y-axis. So you can imagine just different operations working on this block sphere. So in order to motivate the actual how we're going to do the Mermin experiment, what we do is we propose a projector that has a custom rotation around the y-axis by a certain amount. So say like an amount theta, and then we actually give the matrix form of it here, where r of theta is equal to this operator. We don't really need to know about the matrix form because Qiskit actually has a rotation around the y-axis operator built inside of it. But what we do need to do is we build this projector and we measure it on a certain like qubit, either 0 or 1, and we need that to be our state kind of built into the projector. So we have a projector buildup of this rotation matrix and then some sort of qubits, either 0 or 1. Here we're using an example of 0 last week in the November 16th slides. But then to use this projector and get the probability, we need to use the standard form of the projector probability, where we do something like psi, then the projector, and then another psi, all of this bracket notation. So here we're denoting this r theta 0 with some like any custom theta as r0, r0. And we're taking the probabilities, and to get the probability, we just slap r0 projector in the middle of it, and we do this little this little transformation here, going from this line to this line. I know it's hard to read highlighting, but hopefully this is an overview, where we do a transformation that we are able to use measuring in the standard basis here, measuring on 0, as our little trick, because in Qiskit you can only measure in 0 or 1, so we need to make that in terms of a 0 or 1. So doing the complex conjugate of the transpose, the t vector, complex transpose of the rotation matrix there, and bringing it out, we can then just use the 0 basis, so we can just measure as a standard computational basis. So then using this formula, we are able to then implement this in Qiskit using this as like our basis for measurement and everything like that. So any questions off of that, or like the review from last week and how we use the projectors to actually measure things? Okay, great, perfect, thank you. So now, with that in mind, what we're going to want to do is, because in the Mermin experiment, if you remember, we have 3 different settings. Scroll all the way back down here. So 3 different settings, and the way we're going to enact that or kind of recreate that is by measuring in 3 different bases. So we talk about it briefly in the lecture. So since we're dividing like a 360 degrees up, we're going to do at 0 degrees, 120 degrees, and then negative 120 degrees, which is also kind of like the equivalent of 240 degrees because we're just rotating the other way. So those are going to be our three bases where we kind of rotate our axes here, and it's going to be the way that we measure. So we're kind of measuring in a different setting, like analogously. So yeah, let's just hop into Qiskit here, and we'll get started. So I've got two files as a case example. We'll go through and walk through those, although I know you guys are familiar with Python and Qiskit at this point. But we'll start simply. So we're going to start with the case A for the Mermin experiment. The case where the setting is the same here, and actually maybe like this a little bit bigger, because I know reading code is kind of annoying. Yeah, hopefully that should be better, just a little bit better. So yeah, we start by building up a simulator, and then we're going to start with building a QE or EPR pair here. Sorry. So in the circuit, I'll scroll down and kind of reveal it. In the circuit, that's the Hadamard, and then the CX gate right there. So we start with that, and then we're going to pick randomly 3 different settings, or we'll pick 2 different settings, but to be the same because we're dealing with case A here. So because the like actual measurement bases we want to be is going to be the same, we're going to choose a random 0 through 2. This will be like one of our 3 different settings, and then set it to that. So here we denote like if our random integer that we picked is 0, then we're going to just do the identity, which because it's almost as if we're not rotating anything around the matrix, so it's just like the 0 degree point. And then if we are actually rotating it, we use the .ry gate. And then the .ry gate just takes a degree in radians. And I forgot what this other integer is. I actually looked that up really quick. That's the Qiskit quantum circuit ry gate. I'm going to circuit.ry. I've just been searching up these gates, but I forgot what that second, and I should have put that in the documentation. Theta, oh, it's then the qubit, right? Yes, it's the qubit level. So that just applies the same gate to the first qubit at a rotation of 2 pi over 3 radians, and then the same to the the second qubit right there. And then if it's not one of those 2 cases, then we're going to do the minus 120 degree case where we do a circuit at minus 120 degrees. So we're just running the experiment with the same settings because it's simulating case A. Does that make sense?
Yeah, I think I understand.
Okay, yeah. If it doesn't, like reading through the code or like watching it will hopefully make a little bit of sense. Then we're going to throw that into we're going to automate it a little bit. Where we throw it into simulator and run it 1,000 times, and then we're going to print out the total results. So it's going to be like different 0 and 1, 0, 0, 1, 1 that we're going to put in there. So we're at those results. So if we just run it once, you should see the histogram. So this is the case where the rotations is 0, so we just get the identity matrix out, and then we're just measuring it. So we measure 0, 0 the same, like 486 times, and then 1, 1 the same, 514 times, and then it plots it out in this nice little histogram here of both of them. But if we run it again, so this is just running once, and then this is running the whole simulator, and then this is showing the diagram of it. But we run this again. Oh, whoop, that's the identity again. There we go. Here's a case where we got the third setting where it was rotated by minus 120 degrees. So it's the RY gate at minus 2 pi over 3. And then it shows just about the same. So these ratios for the same gates are we're just getting different amounts of 0, 0 and 1, 1. But it's about, they're not changing in any sort of way. It's pretty much the standard classical case A where if we get the same input, we'll get the same input, same output? Sorry, if it's like case A, they'll be the same, is I think what I'm trying to say, if that makes sense. So does that make sense, or any questions on that?
I'm just kind of confused, I guess, with what we should be expecting. So 50-50 makes sense.
Right. So think about it as 0, 0 is like the red, red, and 1, 1 is green, green.
Okay.
So
in case B, we might get 0, 1.
Yeah, we might get a mix. So actually, I'll skip ahead to it. It'll be 0, 1 or 1, 0 will be red, green, or green, red, or red, red, or green, green.
Okay.
Yeah, exactly. So yeah, we're just starting with the simpler case where it's just red, red, or green, green, because that's kind of built into our assumption for case A, if that makes sense.
So then for case B, you would be doing where you did the R, we would need 2 R's. We'd need one for the first bit and then one for the second. that.
Absolutely.
Okay.
Yeah, you're right on track, and that is exactly what we're going to do. So if case A makes sense, I'll move on to case B then, and you're absolutely correct. So what we're going to need to do, because it's case B and they're different settings, we're going to have to make sure that they are different gates whenever we run it. So I'll run it again just to, if you believe me. So yeah, we're always going to have a 2 pi over 3 and a minus 2 pi, so we need to explicitly make sure that we have two separate gates that are being run in the Mermin experiment. So we'll do that up here. Oh yeah, I forgot that the identity gate, I ran into a bug when I was working off of, this is based on Dr. Sarber's code. Apparently the .ident is deprecated, so now it's called .id. You probably won't run into that, so just call it ID, because I'm assuming we're using the most recent version of Qiskit. But we are running, again, picking a random integer for the first one, and then a random integer for the second one. I forgot why we were choosing only in a range of 0 and 1. I think it's because of the way he does his if-else statements. Because we basically pick the first one, and then we choose based on the first one what the second one is going to be. So, but I will check that. Because yeah, I think we do the case of 0 where it's equal to 0, and then a case when it's equal to 1.
Oh, because it can't be the same.
Yeah.
Yeah. So
yeah.
Okay, so that's how we did it to make sure that they weren't the same.
Yeah, I guess that makes sense. So yeah, basically it's like all the different cases, and then yeah, if we get the first one is 0, then it's the first bit is identity, and then if the second random integer is 0, then it builds the 2 pi over 2 on the second bit, and then if not, we just did the minus 2 pi. So yeah, this is just running through the 3 different cases where hopefully it should be making sure that, so the example, this one, or a rotation by 120 degrees, then the first one, it'll be ID on the second bit, and then if not, it'll be minus 120 degrees on the second bit. And then the third case where just the opposite of here. So just making sure all 3 are different cases. And then again, we're going to run it through the simulator and crack up the results. And in this case, we should be now expecting some mixes of colors in our flashing lights, like I said before. So we'll have, let's say 0, 0 is red, or 0 equals red. We'll have some red, 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 green, green, red, and then green, green in our different counts. So let's run that through. And yes, absolutely. So we can see, so we're counting up our counts, at least for one simulation, where we have the identity, and then the minus 120 degrees. We have, let's start with 0, 0, 134 counts for 0, 0, 381 counts for 0, 1, and then 360 for 1, 0, and 125 for 1, 1. So if we're counting out the cases, and hopefully you might be able to see right off the top of your head, but if we're counting out the probabilities that we get the same case in case B, that should be 0.134 plus 0.125. So that is just a little bit over a quarter of the cases are being the same when the settings are different. Just to verify that they are different, we will add up the second case. So yeah, just a little bit under 3/4 in the case where they are different settings. So if you remember from the original Mermin experiment, and actually I'll pull it up, I'll pull up my Excel, even though that's not the most readable, but if you're, actually I'll just go to it in the actual paper itself. When we did it classically a couple weeks ago, the actual thing was that we counted at least over 1/3, but it was actually more like a half, which you pointed out, Chris, that it should be a half of them should be the same for case B. But now when we run it, let me see if I can find the paragraph. I think it was case B, case A, just for putting something on the screen. There it is. Here it is. Yes. So yeah, talking about the different probabilities. So in actuality, it is when we run it through a quantum simulator, it's 1/4 of the cases are the same, and then 3/4 are not the same, which is way lower than our classical result when we actually simulated using our classical identity. So yeah, we see now the problem at hand and how the Mermin experiment works out. I'll bring up my case. Yes, no, yeah, I just remembering from, yeah, I got, when I was running at least for a batch 100, I was getting about 50-50 for our case B's last time. So that is absolutely where we're at. So that is the Mermin experiment, the quantum Mermin experiment in a nutshell. So any questions based on that so far? Hopefully that makes sense. Okay, perfect. So I actually don't have anything else for this tutorial today, so I'm sorry, it is extremely short. and I could have just sent out the code. So I'm sorry for you, Chris, that have come all this way just for a short tutorial, but hopefully that is okay.
We don't have to code in?
Yeah, no, there's no take home this week either. I've been meaning to grade the last two take homes, and I couldn't think of anything to come up for a take home today, so it's going to be a very short tutorial this week. And hopefully, I know you guys have the project to work on and other assignments, so hopefully that just gives you a little bit more time to work on those. But if you do feel free, I can post this code and you can play around with it if you want to see, or play around the rotation matrices. But it hopefully is straightforward after an explanation on how we are simulating this experiment and encoding it into a quantum simulator. So, yeah. So hopefully that is all good. All right, perfect. All right, well, thanks for watching, and another short one, but have a great week.